So in this video, we're going to take a little bit of time to talk about the 30-60-90 right triangle ratio. This is something that if you're taking a trig course moving on to a calculus course, I'm guessing your teacher or your professor is going to ask you to memorize. It's something that you really need to know if you're going to have success in utilizing the unit circle without necessarily using a reference sheet in order to use the unit circle. But we'll go ahead and get right into it here. If you look at this triangle on the left side of the screen, it is a right triangle, pretty obviously. It does have a 30-degree angle. It does have a 60-degree angle. So it is definitely a right triangle. If you look at the measures of these sides, the smaller leg measures 1 unit. The larger leg measures square root of 3 units. And then the hypotenuse of this triangle is going to measure as 2 units. Checking the Pythagorean theorem real quickly, if I take this leg squared, I still get a 1. If I take this leg squared, squaring the square root gets rid of the square root, so I just get 3. 1 plus 3 is 4. That's got to equal this side squared. Square root of 4 is 2. Yeah, it does. So this is definitely a right triangle. We've confirmed it by double checking the Pythagorean theorem. This right here, 1, 2, square root of 3, is how I've always taught my students to try to memorize this ratio. So if you have a 30, 60, 90 right triangle, what you are guaranteed to have is the ratio between the sides is 1 to 2 to square root of 3. You do have to recognize which of these values is the largest, and it's actually the one in the middle. I've seen people make mistakes in the past and think, well, 3 is bigger than 2, so the square root of 3 is bigger than 2. Definitely not the case, right? Square root of 4 is 2. So although it might not look like it, 2 is definitely a larger value than the square root of 3 is. So 1, 2, square root of 3. How do we utilize this? Well, you might be doing problems like the one that we're going to look at next. So what I've done is I've basically just enlarged this triangle and I've re-established what the measure of the hypotenuse is. So rather than a hypotenuse of 2, this hypotenuse is going to have a measure of 5 units. Now, what we don't know is we don't know what the measure of either of the legs of this triangle would be. What I did is I went ahead and I wrote out my ratio, right? The side that corresponded to the side that initially measured 1, the smallest side of the right triangle, is the side I'm going to write first. So I just used the variable x to represent that. My hypotenuse is listed in the middle, so I do know the hypotenuse of this triangle. It's a 5. So I tossed a 5 in the middle of that ratio. And then as my final side, the larger leg on the base 30, 60, 90 triangle, it was measure square root of 3. I don't know that here, but I am going to put that corresponding side as the final value within my ratio, and I'm going to use the variable y to represent it. Now here's what you need to recognize. This triangle, the smaller of the two, and this triangle, they're similar to each other. The reason why they're similar is through angle-angle, which can also be called angle-angle-angle. So depending on your teacher, how you learned it in geometry, you might say AA for angle-angle or AAA, angle-angle-angle. If 2 of the angles of a triangle are the same, the third one has to be the same as the other triangle, right? Because they all have to sum to 180. So we're definitely looking at similar triangles here through the angle-angle or angle-angle-angle postulate. So let's think about how we might be able to use that to our advantage. I have 2 methods of solving this here. I'll show you the method that I used. And I showed this method first because when you use the unit circle, which is what my students are going to be ramping up to do with this stuff in the next few lessons, when you use the unit circle, it's a little more convenient to just have the ratio written in terms of this triple as I have it right here. So what I did is I said, well, I know that there's the values here are proportional to the values in this ratio, right? These ratios have to reduce to the same thing. They have to both reduce to this base ratio. So what I tried to think is okay, well, what's the constant of proportionality that I multiply this hypotenuse by to generate the new hypotenuse, right? So I'm going to take the original hypotenuse, I'm going to multiply by some constant, and I'm going to generate the new hypotenuse. What's the value of that constant have to be? So pretty quickly, I was able to solve that for that constant of proportionality, which I used the constant k in order to represent. So I got my constant of proportionality to be 5/2. So what I then realized is I should be able to take 1, multiply it by k to generate x, right? So 1 times k has to equal x. Well, if I replace this k with what I just got for the value of that constant of proportionality a few seconds ago, 1 times 5/2 is just 5/2. So my measure for side x is going to be 5/2. And then I'm doing the same thing with the larger leg, right? So my base ratio has a larger leg measuring square root of 3 units. I'm going to multiply that by that same constant of proportionality k, and that's going to give me my new side y. Well, if I take square root of 3, and as a fraction, this would be over 1, right? Square root of 3 over 1 times 5 over 2. If I multiply the numerators together, multiply the denominators together, I get 5 square root of 3 over 2. So here would be my new measures for the sides of that new right triangle. That's also a 30, 60, 90 right triangle. If you're more comfortable with this, you can use the familiar method of setting up a proportion between corresponding sides of the similar triangles. So I took the proportion between the hypotenusi, I believe would be the plural of hypotenuse, which was 2 on the smaller triangle divided by 5 on the bigger triangle. That's got to equal and notice how I have the smaller triangle measure kept in the numerator of this proportion that I'm setting up. So I have 1 as the smaller leg on the smaller triangle divided by x, which is, if I scroll back up, didn't mean to highlight that. If I scroll back up, that is the smaller leg on the new right triangle. If I solve this, and it's pretty easy to solve, if I multiply, cross multiply here, I'm going to get 2x on the left. When I do the multiplication on this diagonal, I'm going to get 5 on the right. Well, if I have 2x equals 5, divide both sides by 2, and I get 5 halves. And I'm going to get a similar situation here. If I cross multiply and solve, I'm going to get the same answer as I got for y. So whichever way you're more comfortable with solving it. If you're going to be using the unit circle, it's probably good to kind of get familiar with this constant of proportionality idea. If you're more comfortable setting up the proportion and solving it that way, you can definitely do that. Last thing I want to say within this video is if you are taking the SAT, they do provide you with this information in a slightly different form than we just looked at it within on the reference sheet for the SAT. So what they provide you with on the reference sheet is if you have a 30, 60, 90 right triangle and the smaller leg measures x units, the hypotenuse is going to be double x, and then the bigger leg is going to be whatever the value of x is times the square root of 3. If you'll notice, the values that we just looked at are present here. We've got the 2 there, we've got the square root of 3 here. And if I wanted to, I can toss a 1 in as the coefficient of x, right? And there's the 1. So there's the 1, the 2, the square root of 3. On the SAT reference sheet, they've kind of represented it in a similar way to how I was using that constant of proportionality, right? I had k as the linking factor between, or the linking constant of proportionality between these 3 sides. They're just choosing to use the variable x to represent that. So it's just represented a little differently, but you use the information the same way. So like I mentioned a little earlier in the video, if you are going to be using the unit circle, and the reason why you're learning these 30, 60, 90 ratios is to be able to utilize the unit circle, you're going to want to memorize them. But for the purpose of the SAT, you're going to have access to this little diagram as you see on the screen right here. In the next video, we are going to talk about the other significant ratio that you would need to use in order to use the unit circle, and it's also provided on the SAT, and that is for a 45, 45, 90 right triangle.